Welcome back to another video. In this tutorial, we are going to look at how we can understand the concept of exact differential equations. Right here, trust me, I'm going to break this concept into smaller bases for every individual to understand the concept behind the exact differential equations. Note, the differential equations as a whole looks complicated in general to many others out there. But trust me, this is going to be very simple for everybody to understand. One, what you have to understand about differential equations is that differential equations are just equations that involves derivatives, right? So once you hear the word differential equations, you have to think about equations that are involving derivatives. So right here, we are going to talk about the exact differential equations. We have, for the first order differential equations, we have the separable method, we have the homogeneous method, we have the integrating factor or the linear approach, and then we have the exact differential equation. So right here, what we are going to delve inside into details is the exact differential equations. Anyway, I have videos on the other methods, right? The first order, the other methods, the separable, the homogeneous, and the integrating factor or the linear method. Everything is inside there. So check out the link and we'll be right with you. Good. So with this exact differential equations, this is how it is. We have m of x and y dx plus n of x and y dy is equal to 0. So this is how the equation is being quantified to be part of exact differential equation. So once you have something like this, then you have to begin to think about exact differential equation. So this equation will only be exact, okay? If you have an equation in this form, it will only be exact if and only if you take the derivative of this particular one right here with respect to y, and you take the derivative with respect to of this particular one right here with respect to x, and they are all having the same result, then you can say that that particular equation is indeed an exact differential equation. So right here, we're going to take derivative of this one with respect to y. Okay, so with respect to y, derivative of m of x and y, right? So derivative of m of x and y with respect to y, right? Okay, should be equal to the derivative of n of x and y with respect to x. This result should be giving you 0, or they should be equal. Basically, they should be equal. So if the derivative of this first equation with respect to y is equal to the derivative of the second part of the equation is having the same argument, then you can say that that particular equation satisfies the requirements of being part of exact differential equation. So let's look at an example to check that particular condition. Okay, so an example is 2x y plus 1, right, plus x squared plus 4y y prime, right? And this is equal to 0. So right here, we can notice that this equation is of this form, right? It's identically of this form, but we have to change this y prime for it to look like this exactly. Okay, so here y prime is basically equal to dy over the x, right? So once you have this, then you can say that 2xy plus 1 plus x squared plus 4y dy dx is equal to 0. So you know that you can multiply through by the x so that you can have something of this form. So you have 2xy plus 1 dx plus s squared 4y dy is equal to 0. Okay, so this we have right here. We are going to differentiate this particular function with respect to y. Then we differentiate this one with respect to x. If both terms gives us the same result, then we can conclude that this particular equation is indeed an exact differential equation. Okay, so this we represent the first term as m of x and y, okay, equals as m of x and y equals 2xy plus 1 dx, right? Then n of x and y equals 2s squared plus 4y dy. Okay, so this one, m of x and y equals 2xy plus 1 dx, we are going to differentiate it with respect to y, So here we are going to have d of mx and y with respect to y is going to be, when you differentiate 2xy plus 1 with respect to y, we are going to have 2x. So this is basically equals to 2x. Okay, so once we have that, then we go for the other one, differential of n of x and y with respect to x. Okay, so this part with respect to x, we are going to have also 2x. Okay, so once we have differential of the first term, okay, to be 2x and the second term to be 2x, then we can conclude that certainly this particular equation is indeed an exact differential equation. So therefore d of m, x, and y, differential of this is equal to this over vs, and that is basically equal to 2x. So this is indeed an exact differential equation. So once this satisfies, then you can go ahead and use this particular equation, then solve for the differential equation. Okay, so let's go through the process or the methods that we can use to solve an exact differential equation. So the first method, okay, so methods for solving um, exact differential equation. Methods for solving exact differential equation. So the first method is if the equation is y is equal to dn of x and y over the x holds or satisfies or works, okay, then we can say that there exists a function. Okay, so there exists a function, say f of x and y, and that function, this particular function, there exists a function f of x and y such that such that the first differential of the function with respect to x, okay, the first differential of the function with respect to x of x and y is equal to m of x and y. And that should be named equation 1. 2, f of y, that is the first differential with respect to y of x and y, is equal to n of x and y. And that should be named equation 2. So the condition is, if you have the equation and you check for exactness and it works, okay, then it means there exists a function, say f of x and y, such that that particular function, its first derivative with respect to x of the two variables x and y is equal to m of x and y. We have equation 1 and equation 2. Now the ball is in your court. The ball is in your court. You either decide to integrate equation 1 with respect to x, or you integrate equation 2 with respect to y. So here I'm considering the equation 1 to integrate. So I'm going to integrate equation 1 with respect to x. Okay, so 2x plus 2y squared vx. So here, when you integrate this, you're going to have 4 f of x and y. This first derivative, basically this and this will go. Okay, so we have f of x and y is equal to, when you integrate 2x plus 2y squared with respect to x, you are going to have 2x squared over 2 plus 2xy squared plus, here we are not going to add a constant of integration c, but rather phi of y, phi of y. So here we have phi of y. So let's break it down and name it equation 3. So f of x and y is equal to, this cancels this, so we have s squared plus 2x y squared plus phi of y. So let's consider this as equation 3. Now, in order for us to get our phi of y, what we do is that we differentiate this equation 3 partially with respect to y. So when we do that, differential of equation 3 partially with respect to y, okay, so that will be equal to differential of this partially with respect to y. Okay, so that is basically going to be partially with respect to y, means that this s term will go, and we're going to have, we name this equation 4. Okay, so and equation 4 are the same, we can equate them. So equate equation 2 and equation 4. So you see we have equation 2, f y of x and y equals 4xy plus 3y squared, and we have fy of x and y equals 4xy plus phi prime of y. So since we have this and we have this, then we can equate their right hand side term. So we are going to have 4xy plus 3y squared equals 4xy plus phi prime of y. Okay, so this can be simplified to 3y squared equals phi prime of y. So this is what we have now. So let's say this is equation 5. Okay, so once we have this, then the next thing to do is we have to integrate this. So once we integrate this, then we can have our phi of y. So we have to integrate this. So integrate equation 5. So we integrate this 3y squared with respect to y is equal to integral phi prime of y with respect to y. Okay, so when you integrate 3y squared, you're going to have 3y cubed over 3. Okay, and that is plus a constant of integration, right? So that one we can say C1. Okay, that is equal to, when you integrate phi prime of y dy, you're going to have phi of y. Okay, so this takes off this. So we have, let's bring this here. So we have phi of y equals y prime plus a constant, say C1. Okay, so once we have phi of y equals y cubed plus C1, the next thing we have to do is that put equation 5 into equation 3. And that is what we have here. This is equation 3. And this is equation, let's name this one equation 6. So this is equation 6 and this is equation 3. So let's try to put equation 6 into equation 3, because we have phi of y equals y cubed plus C1, and then we have phi of y here. So let's try to put the phi, the function of phi into equation 3. So when we do that, when we do that, then we're going to have f, x, and y will be equal to x squared plus 2xy squared plus, now our phi of y is y cubed plus C1. So we're going to have y cubed plus C1. Okay, so once we have this, we can now say that, can we do something about it? Can we do something about it? Can we do something about it? Okay, so from here, since gradually, what we are interested, we have been able to get it. What we do is that this is basically nothing we can do about that anyway. So basically, we know that, but f of x and y is equal to c. Okay, so once we know that this is this, then we can say that c is equal to s squared plus 2xy squared plus y cubed plus c1. Okay, so once we know that this is a constant, this is a constant, so we can combine them and choose one. Okay, so we can say that let c equals c minus c1, or you can say that let k, right, they are all the same, so let k equals c minus c1, because when you bring this, you're going to be c minus c1. So we're going to say that k is equal to s squared plus 2xy squared plus y cubed. So ladies and gentlemen, this is the end of the problem. So this becomes our final solution to this particular problem. but we have been given an initial. Okay, so this is the general solution. This is the general solution to the differential equation that we had. Okay, so we have been given initials. We have been given initials that that the initials are y of 0 is equal to positive 1. Okay, so what does this mean? This is basically telling you that they want you to find the constant. Okay, so the constant over here, we are going to look for it. So this statement means that our y is equal to 1 and our x is equal to 0. So we substitute this information into the particular solution. This is, sorry, this is the general solution. Then we get our particular solution or the specific solution. So here, our k will be equal to x now is 0. So we have 0 squared plus 2 into 0 into 1 squared plus 1 cubed. Okay, so we're going to have k equals 0 here, 0. 0 of everything is 0. Then we have last one to be 1. So we have our k to be positive 1. So once we have k to be positive 1, we substitute into the general solution to get our particular solution. So here we can say that our k, which is equal to 1, is replacing this here so that we can have our particular solution. So we have 1 is equal to x squared plus 2xy squared plus y cubed. Okay, so this becomes our particular solution. This becomes our particular solution. So we can rewrite this as x squared plus 2xy squared plus y cubed equals 1. So this is the particular solution obtained for this particular differential equation. Ladies and gentlemen, don't forget to subscribe, share with your mates, and I'm going to give you more updates. You know, the process, okay, you just have to keep watching and you understand all the concepts, because this differential equations looks a little bit challenging to many of students or many students. So but once you keep practicing the methods or the process that we go through to handle the problem becomes part of you, right? You know, continuous doing of everything becomes addicted, or you become addicted to it. So continue practicing and it's going to be part of you. Thank you very much. Bye bye.